SwayamPrabha. Digital India. Educated India.
So, this will be lecture number 46 in our ongoing set of lectures on mechanical measurements. So, toward the end of the last lecture, we are actually looking at the measurement of force, and we will resume from there. In fact, we were discussing different ways of measuring force, and one of the ways of measuring is to use a spring element, and we discussed a few typical cases where this force is estimated by looking at the displacement in a spring element. We will also look at force balancing, or using balance of forces to measure the force. So, these are the two things we are going to look at in this lecture, and then we look at the very important application of force measurement to the study of vibration and the measurement of acceleration. So, we will try to set forth the principles of operation of vibration and acceleration measurement devices, and then we will discuss a few methods which can be used for that. However, to start with, let us look at force measurement, and this is a slide which I used in the last lecture also. It simply says that one of the simplest methods is to use a transducer that transforms force to displacement. So, displacement is a measured quantity and the force is the inferred quantity or the estimated quantity. A spring element may actually be a spring, like in a spring balance, or it could be an elastic member which undergoes a strain under the action of the force, and the strain is measured using, for example, a strain gauge, which was discussed earlier when we were discussing pressure measurement. So, let us look at an example to bring home some of the ideas. So, I take the case of a cantilever beam, which was actually given as an example in the last lecture. It is made of spring steel whose Young's modulus is 200 gigapascals. GPa stands for gigapascals, that is 210 to the power of 9 pascals. It is 25 millimeter long, has a width of 2 millimeters. It is in the form of a beam and thickness of 0.8 millimeters. So, we want to determine the spring constant for this particular case. And the second part of the question says that if all the lengths are subjected to measurement uncertainties of 0.5%, we want to determine the percent uncertainty in the estimated spring constant. Thirdly, if the displacement which is measured under a force acting at the tip of the cantilever beam is 3 millimeters, what is the force corresponding to that displacement? So, we would also like to know, because all the measurements are susceptible to error, what is the uncertainty in the estimated force if the deflection itself is measured with an uncertainty of 0.5%. So, let us look at the following sketch, which shows the type of thing which is happening. You have a beam in the form of a small strip of spring steel. This end is fixed and we are applying the load at the other extreme, and the consequence of that is that this end is going to deflect by a certain amount in the downward direction. So, that displacement is actually measured. In fact, in this case we can even use a simple vernier scale and measure the deflection easily. So, the breadth of the beam is P equal to 2 millimeters, the length is 25 millimeters, and the height h of the beam, which is the same as this, is 0.8 millimeters. So, what I have shown here is the shape of the beam before loading, that is the straight thing here, and the shape of beam after deformation, it has bent like this. So, essentially the element is a beam element and the beam undergoes a bending, and therefore, this displacement of the free end is actually given by a well known formula from strength of materials, which we will borrow, and we will try to solve the problem on the board. So, let us look at the solution. So, we are given the material property as E equal to 200 gigapascal, which will be 200 to the power of 9 pascals. Then we have the width is B is 2 millimeters. I will convert everything into SI units. So, this becomes 0.002 meter, and the thickness of the beam H is 0.8 millimeter, which will be 0.308 meter. The length of the beam is given as 25 millimeters, which is 0.025 meter. So, we can calculate the moment of inertia of the section. Moment of inertia of the cross section is given by BH cube by 12, where B is the breadth, H is the thickness, and BH cube by 12 is the moment of inertia, which is given by 0.002 into 0.0008 cube divided by 12, and this works out to 8.5333 into 10 to the power of minus 14 meter raised to the power of 4. So, we have the moment of inertia, because the spring constant actually is given by a simple formula. The spring constant, which is what we are trying to find out, is given by, let us use the symbol K, it is nothing but 3 EI by L cube, and this will be 3 into E is 200 in 10 to the power of 9 into I is this quantity 8.5333 in 10 to the power of minus 14 divided by 0.025 whole cube. The unit of K will be newtons per meter. We can actually verify that EI by L cube, this is gigapascals or pascals, this is in meter to the power of 4, and this meter cube, you can show that it is equal to newtons per meter, which is going to be 3277 newtons per meter. So, that is the first quantity of interest to us. We wanted to calculate the spring constant for this particular application, where the load is applied at the free end of a cantilever beam made of spring steel of the given dimensions. So, now we have to calculate the error in the value of K as given by this formula, because all the lengths measured in the problem are susceptible to errors, and because the formula involve mostly products and products of powers, we can use the logarithmic differentiation which we are familiar with, and therefore, directly I can work with the percentage error. For example, the error in percent of the moment of inertia is given by BD cube by 12. So, delta B by in percentage whole squared, this is in percentage, plus 3 times delta H by H, both in percentages whole squared, because of the reason that I is equal to B H cube by 12 is in the ratio of nature of product of quantities and raised to the power. Therefore, I can use logarithmic differentiation and obtain this one. So, delta I by I percent is equal to this, and therefore, delta B by B is simply 0.5%. So, 0.5% I can directly put here under root of plus 3 into 0.5 whole squared. This gives you a value of 1.58%. So, the moment of inertia is in error by 1.58%, and if you remember the formula k equal to 3 EI by L cube, I is now in error by 1.58%, L is also in error by the same percentage. Therefore, now I can use a similar formula and assume that E itself has no error specified on it. Therefore, we will assume that the error is only due to measurement of various lengths. So, we can say now, because of this, delta k by k in percentage, it will be simply given by, it is 3 EI by 3 is simply a constant, E is also now assumed to be having no error. So, this becomes delta I by I percent whole squared plus L cube, that will give you 3 delta L by L whole square. That will give you again 1.58 square plus 3 into 0.5 whole squared. This is in percentage, and this will give you 2.18%. So, the error in the value of the estimated value of the spring constant is about 2%. So, that is the first answer we required, and therefore, we can say k equal to, now using this 3277, that is the value of k obtained, plus or minus 2.18% of that value, that comes to 71.4 Newton meter per meter. So, that is the answer to the first part of the problem. Now, we know that the deflection under the load, if I call it, is 3 millimeter, is 0.003 meter deflection under the load. Therefore, the force which gave rise to this particular thing is ky by definition of spring constant, that will be 3277. I am only giving the nominal value multiplied by 0.003. This will be so many newtons, and that works out to 9.83 Newton. So, that is the force that has been applied, and that gave rise to a displacement of 3 millimeters under the load. And again I can use the same, k is susceptible to error, we already know, y is also susceptible to error. Therefore, I can also calculate delta f by f in percentage is equal to square root of delta k by k in percentage whole squared plus delta y by y percent whole squared. So, this will give you square root of delta k by k percent is actually 2.18 whole squared plus this will be 0.5 whole squared, and therefore, the percentage error in the force measured is plus or minus 2.24%. So, the error in the measured value of the force is given by 2.24%, and therefore, I can actually calculate what is the force which has been estimated what is the error in the force. Therefore, I can also say F is equal to 9.83, that is the value which we got, plus or minus 2.24% of that, that comes to 0.22 Newton. This is the answer to the problem. So, you see that in this example the elastic member which undergoes a deflection, which is in the form of a cantilever beam made of spring steel, can measure a force of about 10 newtons. 9.83 is very close to 10 newton for a deflection of about 3 millimeters under the load. So, this is just an example to show what kind of numbers you expect in a problem like this. Now, we will go back to the slides. Having solved this problem, let us look at force measurement by other methods. For example, we can measure force by mechanical balancing using simple elements such as the lever, and in fact in the last lecture itself I mentioned that a platform balance is an example where the force measurement is actually used, force measurement by balancing is used for determining the mass of an object. In fact, you can take the case of a simple balance. The simple balance, we have a horizontal member which is balanced at the center of the member, and on the two sides there are two pans, and in each pan you put the weight, and one pan you put the weight, in the other pan you put a mass of the quantity, the mass of the object whose mass you want to measure, and then you find out when there is balance. That means that the horizontal arm of the balance must be perfectly horizontal. That is usually indicated by a needle attached at the center, whose verticality you note against a scale. And there what we are doing is we are balancing, actually the mass is measured by balancing a known weight or a weight of an object whose weight has to be determined with respect to a known weight which is calibrated, whose weight is known, and by balancing you are able to find out what is the mass. Because both the pans are subjected to the same gravitational force, gravitational acceleration, same gravity is acting on both the sides, and therefore it is actually the force balance, it is actually the moment balance. The moment of one force on one of the pans is the same as the moment because of the other force in the other pan of the balance. So, similar thing can be done by using what is called a platform balance, which is used usually for measurement of very large masses, or if you want to call it very large weight. So, the principle of such a balance I am going to explain on the board by taking a simple schematic of such an arrangement, and what I have done is I have drawn this schematic here, and let me just explain what are the things which consist of. This is the platform, what you see here is the platform, and the weight can be put anywhere on the platform. That is the whole point of this platform balance. It can be placed anywhere on the platform. There are two knife edges which rest on, one of these knife edges rests on this beam, and the other one rests on this beam. There are three beams, as you can see, one here, two here, and a third one here. So, this is resting here, and the force is applied here, and you can see what is going to happen. This force is distributed here and here. These two forces W1 and W2 are due to W, which may be placed anywhere on the balance. Of course, W1 plus W2 must be equal to W. Okay, W1 and W2 itself is determined by the position of W, depending on where it is put. W1 and W2 will be different amounts. We need not worry about that, that is the whole point here. So, this rests on a knife edge here, and you can see that this beam also rests on the third one. The third member has got the W2 coming here at a distance of h from this knife edge, and you can see that this is resting here. There is another force coming at a distance equal to E, and then you see that this is attached to a vertical arm vertical rod. This rod is going to be either pulled down or pushed up, depending on the whether balance is there or not, which way is the balance. So what happens, this there is a certain force in this member, and this is applied to, there is a knife edge here and this is the knife edge. This thing here is going to be, this force is applied one here, and there is a counterpoise, and this is the fulcrum, and this is another lever here, and the weight Ws is going to be put here at a distance equal to A from this fulcrum, and the force T which is in this member is applied, is acting at a distance B from this place. Okay. So we can analyze this very easily by going through part by part, and let us look at what are the equations we are going to get. It is just a balance of moments. So you can see here, if you apply it to this member here, this member, Ws into A, that is the moment acting in the clockwise direction, must be equal to T multiplied by B, which is acting in the counterclockwise direction, if there is a balance, if the balance is there. Okay. The balance is usually indicated by a needle here, which can be, whose position is going to indicate whether it is balanced or not. So T into B equal to Ws into A. Ws is the weight, which is now going to be the known weight. We know what this Ws is. The next equation is, if you look at this member, there are several moments on that, and you can take moments about this particular point. So the sum of the moments must be equal to 0 for the balance of that. So T into C, the T is this force here, multiplied by this C is the force acting on it, the moment. This must be balanced by, so W2 is acting, you can see here, W2 is acting here at a distance h, W2 into h, plus W1 is acting here, and there is another lever here. Therefore there is a factor of F into E by D. E is this distance, this F divided by this F by D comes from this lever. Okay. Therefore what we have is T into C equal to W2 into h plus W1 into F into E by D. I can rearrange this equation by writing for T equal to E by C. I will take E outside here. So this will be E by C multiplied by W2 into h by E plus W1 into F by D. Suppose we arrange h by E equal to F by D, because this is something which we can choose. H by E equal to F by D, if we choose, these two factors are the same. So you see that if I take h by E outside, it becomes E by C into h by E into W1 plus W2, which is nothing but W. So this becomes, E will cancel off, HW divided by C. Okay. This is equal to T. So I can write here, T equal to Ws A by B is also equal to H, this formula. So these two are equal, and therefore I can calculate W. So I will write it here, W equal to Ws A by B into C by H into Ws. So W, which is to be measured, which can be placed anywhere on the platform, is equal to the product of A by B, C by H. These are all constants, and this A into C divided by B into H is the gauge constant. Therefore Ws, the value of Ws itself directly gives you W by multiplying it by a product, which is a gauge constant, which is chosen once we have all the lengths A, B, C, H are determined, are known, then we can calculate the gauge constant directly. So, this is how you get the weight. So, weight is obtained by in terms of the added weight at the in the pan. Apart from this, we also have a small weight which can be moved here on this arm. This is called the Poise weight. We also have what is called a counterpoise weight, which is on this side. This is all this counterpoise is used actually to balance the instrument, balance when there is no load on it, we want to balance it. So, that can be done by the adjustable counterpoise. Now, you can see what happens if I put a poise weight here, it is like putting a smaller weight here, because this is Ws, Wp, the moment arm is only this portion, whereas the moment arm for this is much larger. Therefore, it is going to give me a control. For example, if Ws is 10 kilograms and I want an improvement in the measurement in terms of less than 100 grams, I want to measure using this, I can use a weight here at a smaller distance. So, that gives you a smaller least count of the instrument goes up, and this can be moved on a scale, and therefore, I can find out the scale reading here will correspond to a smaller weight. So, that is the way it works. So, the platform balance is simply an instrument where force is measured. Force in this case happens to be the weight of the material which I am going to put it here, is measured in terms of balancing of the various moments acting on members, and what we have seen is that the position of W on this platform is the material. Wherever you place it on the platform, it is going to read the same value. So, this is an example which is indicative of another way of measuring the force. So, now let us go back to the slide and see what is the next thing which we are interested in. So, we are interested in measuring acceleration, and an accelerometer or a meter measuring the acceleration of a member or a mass is called the accelerometer. It could be the acceleration may be due to vibration of a machine, for example, and we would like to measure the acceleration because of the vibration. Or if we have an instrument, we would like to find out how much vibration it can withstand. I would like to find out what is the acceleration it is subjected to during these vibrations. The measurement of acceleration is one measurement which we do to study the vibrational response of a system. We may also be interested in measuring the force which the member experiences because of vibration. We may be also interested in the displacement because of the vibration. There are many aspects which need to be measured, and let us look at some of these things. If I have a mass and an acceleration is imposed on it, it means there is a force which it gives rise to. So, the force is nothing but mass into acceleration. An acceleration imposed on a mass gives rise to a force, and in fact, this force may be measured to estimate the acceleration, because acceleration is not directly measured. The force can be measured by using any of the methods we have just now discussed. For example, a spring can deflect, and the force can be measured with the spring, and from that I can find out what the corresponding acceleration is, if I know the mass which is undergoing the acceleration. Okay, that is how you work it out. For example, a seismic acceleration measurement or seismic accelerometer is based on this principle. Secondly, as I talked about vibration measurement, it involves measurement of amplitude of the input waveform, and the input waveform may be any waveform. It need not be sinusoidal, it could be non-sinusoidal. So, that is one complexity which is going to come when you want to measure the vibration amplitude. For this purpose also I can use a spring mass system, or in fact I am going to describe later a non-intrusive measurement using laser Doppler vibrometer. This laser Doppler vibrometer is just like the laser Doppler velocimeter which was used in the measurement of velocity of a fluid. So, similar principles are going to be involved, but we can use a laser Doppler vibrometer to measure vibration. So, what I will do now is to look at some of the basic principles involved, especially in the case of spring mass system. a typical spring mass system is shown here. This is a mass and there is a spring attached to the mass, and there is a base plate which is in the form of a bent plate like this, and the spring is attached between this and the so. And what I am going to do is I am going to subject this base here to the acceleration. The acceleration is directly applied onto the, if you want you can say that this is the table, and the table is the one which is going to be accelerated. This is like a table on which I got a mass, and for the moment we will assume that there is no friction between the m and this, and the spring is having a spring constant of k. And now when undeflected string means there is no force, there is no acceleration, this will be undeflected. So, m is sitting just there. This length of the spring will be the undeflected length of the spring. If the table accelerates to the right with an acceleration given by a, so the mass, because it is not, it has inertia, the mass will simply stay where it was or almost stay where it was, and the with respect to the mass or with respect to the table, the mass looks like it has gone back. That means that the force is not going to be because of the extension of the spring, the force is felt by the mass, or the mass, because it is staying where it is. Ideal is of course the mass should not move, only the table should move, in which case it will give you the total force will be simply given by the extension of the spring multiplied with the spring constant will directly give the mass times the acceleration, and therefore acceleration is obtained by simply taking the spring deflection multiplied by k and divided by the mass, you will get the acceleration. That is as simple as that. Okay. So, the displacement of the spring is a measure of the acceleration, as you can see. Now, I call it the no damping case because I do not have any damping, there is no damping in this, and we will look at the damped case a little later because that is going to be more important. This is just to explain some of the principles involved. I have taken a spring mass system, and you also know that the spring, if you have a spring mass system without damping, it is having a natural frequency, and when the frequency of if suppose I oscillate or I vibrate this table at a frequency equal to the natural frequency, the displacement of the mass will be enormous. In principle it will go into resonance, and the displacement will be too large, and we do not want that to happen. So, sometimes what we do is we provide two stops. So, if you have a vibrating table and you place the vibration measurement device on top of that. So, what I will do is I will put two stops here, so that the spring is not allowed to extend beyond some value. It will be stopped here, or it will be stopped here on the compression side. So, the motion of the seismic mass, this is called the seismic mass. It is a mass which is more or less isolated from this vibration source. So, it more or less stays in the same position. That is the best, of course, if it can stay in the same position. Then you have the k, the motion is stopped by these stops which are kept here, so that you are preventing the damage to the instrument when the natural frequency of this spring mass system coincides with the impressed vibration frequency. If the same frequency is there, then it will go into resonance. Let us take a simple example, so that we understand some of the numbers as usual, and then we will go back to explaining the nuances of more important things we will discuss afterwards. So, we have an accelerometer which has a seismic mass of mass equal to 0.02 kilogram at 20 grams, and a spring constant equal to 2000 newtons per meter. It is a very heavy, very hard spring, 2000 newtons per meter. The maximum mass displacement is plus or minus 1 centimeter. That means I have provided the stops, so that it will not go beyond that. So, what is the maximum acceleration that may be measured? In fact, we will go back to that sketch in a moment. What is the natural frequency of accelerometer? Let us look at what is going to happen. If I have a stop here, it means that the mass is more or less going to be at the same place. Mass is not going to, it is only the spring is going to extend, and when if it extends, this mass will appear to reach this point. actually the mass is there, the spring extends such that this will come and hit it, and similarly the other side. This is the ideal. Of course, we do not know whether that is going to be happening in practice. Let us look at it a little later when we look at more interesting features of the system. So, we would like to find out this very simple problem, and I will work it out on the board. So, this is example 52, I think. The problem is very simple because the maximum amplitude or maximum movement is given because of the stop. So, that is given by delta x maximum is equal to 1 centimeter. Actually, you can put it as plus or minus 1 centimeter, because it may be either compression or, in other words, the acceleration may be either to the right or to the left, as the case may be. This will be plus or minus 0.01 meter. So, simple A maximum corresponding to this is given by K by M into delta x. K delta x is the force divided by mass is the acceleration, a very simple formula. So, K is given to be 2000. So, I will put a plus or minus because delta x is plus or minus 2000 divided by 0.02 multiplied by 0.01. This will be in meters per second squared. So, that works out to plus or minus 1000 meter per second squared. I just want you to notice the magnitude, it is a very large acceleration. If I actually divide it by the acceleration due to gravity, so 1000 divided by 9.8 into g, 1 g is equal to 9.8. We can see this comes out to plus or minus 102 g. So, if you allow the mass to move about by, or the spring to compress or expand by about 1 centimeter, you are talking about 100 g appearing 100 g as the acceleration impressed, which is a very large acceleration. So, the natural frequency can be also obtained. We know this from our study of mechanics. So, the function, the natural frequency, I will call it as f subscript n. It is nothing but 1 over 2 pi square root of k by m. 2 pi into fn is called the circular frequency, omega n. So, I am just using that formula. So, this will be 1 over 2 pi to square root of 2000 divided by 0.02. This will be in so many hertz, and it works out to about 50.33 hertz. So, the natural frequency of this system is about 50 hertz, and we will see in a little while from now that the natural frequency plays a very important role. And for that, let us look at a more tangible case where you also have some damping, because it is very difficult to have a system without any damping, it is just not possible. So, if you have a damping, the nature of the response of the spring mass damped system is totally different from what we have been talking about. So, in order to look at that, let us go back to the slide shows the schematic of a vibration or acceleration measuring system. For both cases, we are going to use a similar instrument, the vibrometer or the accelerometer, one is the same, but the various quantities m, k, c, etc. I have shown therein are going to be different. So, we will try to look at some of these issues. So, it consists essentially of a housing, the accelerometer or the vibrometer is a housing. This housing has to be attached to the vibrating table or the source whose vibration we want to study. It should be intimately connected with that, and you should not have any relative motion with respect to vibrating table. So, it is necessary to screw it down or attach it in some way, so that it is a part of the vibrating table. So, what I am talking about is only the housing. Inside the housing I have a seismic mass m, just like what we had in the earlier case. I have a spring just as in the other case, but I also have an additional thing shown here. This is a damping arrangement which has got a damping coefficient or damping constant of C. So, the difference between the case we considered earlier and the case we are having now is that there is an additional item coming here. Okay, let us look at what is going to happen. Suppose the table is vibrating up and down. You see that if it is vibrating sideways, nothing is going to happen, because the spring is only able to go up and down, not sideways. So, this will measure the vibration only in this direction, up and down direction. So, accelerometer has directional response, it responds only in this direction. Okay. So, now let us assume that the x1 is the displacement of the table up and down. I have shown up and down arrow because it is vibrating, sometimes it up, sometimes it down, sometimes it goes to the one end, goes to the other end, so on. So, as the vibration goes on, this x1 will go through variations from 0 to a maximum, then again to 0, back to a minimum, and so on. So, it will go up and down like that. So, what will happen because of the movement of this table is the table movement is the same as the movement of the housing. The accelerometer housing undergoes the same movement in step with this x1, and in principle m can go up and down by x2. This is the motion of the mass, seismic mass. Of course, I said earlier that it may be ideal to have the mass x2 0, that means it is standing still. If it is standing still, you can see what is going to happen. The compression of the spring is simply due to the up and down motion of the vibration, and therefore, directly you can find out what is the acceleration or the force, because the spring deflection is what is measured. Okay. So, we will look at the slide again. Can we have the slide, please? So, the mass is undergoing a vibration motion x2 as shown by x2, and let us see what is going to happen schematically. If this goes up by because of x1, this moves by x2, the spring and the dashpot or the spring and the damper are going to undergo a change x2 minus x1. x2 minus x1 is the displacement of the spring as well as this element here. Okay. So, we have to see what is the force on the mass. Mass is of course moving up and down by x2. Therefore, m into acceleration of the mass, which is given by d squared x2 by dt squared, that is the force experienced by the mass. This must be equal to the sum of the forces due to these two elements, because that is what is going to come on that. So, if you recognize that, you will be immediately able to write the appropriate equation, and we can show that the motion of a spring mass system with damping is governed by a second order differential equation, because the acceleration of the mass is going to give rise to a force, and this force is now shared between the spring and the damper. So, that is what we are going to look at, a second order system, and in fact, we have already come across such a system while discussing the transient behavior of U-tube manometer when we are talking about pressure measurement. Therefore, we are going back to that equation, but we are going to interpret the solution in a slightly different way. So, the appropriate equation solution, I am going to work it out on the board, and let us go back to the board and see how to get this. So, the essentially what I have, I can simply show the sketch again, just so that we can recapitulate, we can find out what is happening. This is the housing, there is the seismic mass m, there is a spring, and there is a dashpot here, and this is x1, this is moving up and down x2. So, I want to find out what is the equation governing the change of x2. So, for that we can immediately see that force on the mass because of the acceleration is m d squared x2 by dt squared. So, that is the force experienced by the or because of the movement of the mass. The mass is going to have a force m d squared x2 by dt squared. What is the spring? Spring force is given by k into x1 minus x2, because that is the difference between the two is the displacement of the spring. And similarly, for the damper, we assume that the damping force is proportional to the velocity. In fact, we have done that earlier also, dx1 by dt minus dx2 by dt. So, this is equal to this plus this, that is all what the problem is. Okay. M into d squared x2 by dt squared equal to k into x1 minus x2 plus c into dx1 by dt minus dx2 by dt, and we can rearrange it in the form of a second order equation m d squared x2 by dt squared plus k x plus c dx2 by dt plus k into x2, this will be equal to c dx1 by dt plus k into x1. So, the left hand side I have got all the x2 terms, and the right hand side I have got all the x1 terms. And if you notice, x1 is actually known to us, or it is given as the input. So, we can take x1, for example, I can treat as some x naught cos omega 1 t. This is assumed to be the input from the vibrating table. For the moment I am assuming a single component which is sinusoidal and has got a single frequency. Of course, we can generalize it to any type of input which may not be sinusoidal by using Fourier series. We will look at it slightly later. Now, I am going to impress only one particular frequency if it is shaking with a single input frequency. Now, I can obtain this dx1 by dt from this will be nothing but minus x naught omega 1 sin omega 1 t. Therefore, the right hand side can be written in terms of a given function of t, and x naught will be your amplitude of vibration, amplitude of the vibration. And in a vibration measurement, what I would like to measure is that x naught. X naught is what I want to measure. So, I can write the equation now. I can also divide by m. So, I will have d squared x2 by dt squared plus c by m dx2 by dt plus kx2 divided by m equal to, I am going to divide throughout by m, x naught I will take out as a common factor k by m cos omega 1 t minus c by m omega 1 sin omega 1 t. So, this is the equation whose solution is required if you want to find out what is the response of the system. In fact, the response consists of two parts. as you already know, any second order or any differential equation has got a complementary function and a particular integral, and the complementary function in this case will give rise to a damped oscillation which is transient. The damping will reduce, the transient will go off after some time, and only the steady state part of the solution is important to us, because we want to look at the steady state response of the system. Before we do that, let us introduce some of the quantities which will be useful. So, the natural frequency omega n we already know is square root of k by m. And we will also introduce what is called the critical damping coefficient or damping constant. The critical damping constant C subscript C is square root of 2 square root of k into m, product of k and m. So, with these quantities we can solve the equation very easily, and the general solution I can give for x2 minus x1. The solution x2 minus x1 can be shown to be given by e to the power of minus c by 2m into t into a cos omega t plus b sin omega t, and you notice that the e to the power of minus c by 2m into t, this is the damping part, and it is going to reduce with respect to time. As t increases, this is going to become smaller and smaller, and this is actually the transient part. Which will go to 0 for long time. So, this is not of interest to us, not of interest. We are not interested in that. Plus, this part is a more important one. This is given by m omega 1 squared x naught cos omega 1 t minus phi, where phi is the phase angle, divided by k minus m omega 1 squared whole squared plus c squared omega 1 squared whole thing under the square root sign. So, this we call as the steady state response. And that is what is of interest to us. In fact, what we can do is, in this equation which we have written down, the steady state response, I can divide x2 minus x1 divided by x naught. X naught is the amplitude of the inlet input thing. I can remove cos omega t5. This is just a time factor. So, what is important? X2 minus x1 by x naught equal to this factor. That is the important thing. That is nothing but the response of the system. So, the response of the system in terms of the amplitude x2 minus x1. Of course, x2 minus x1, if it is equal to x naught, we have solved the problem. So, we will say that amplitude response, I will come to the phase angle in a moment from now, is simply given by x2 minus x1 divided by x naught. This is the maximum value of x2 minus x1 with respect to x naught. This can be shown to be equal to, I will also introduce the omega n squared, that was the natural frequency, and then we also had the critical constant, critical value C c, which was introduced earlier. Using that and then rearranging the equation, we can show that this is equal to omega 1 divided by omega n whole square divided by 1 minus omega 1 by omega n whole square, again square of that, plus 2 into c by c c into omega by 1 by omega n whole square whole under the square root sign. That is your response function. We will call that as equation number 1. This is very important, and therefore, I am going to use this as the equation 1. That gives you the response, amplitude response of the system, and the amplitude response you can see is dependent on the omega. It depends on the ratio of C and Cc, and also it depends on the natural frequency. So, for a given system with that means that C is known, K is known, M is known. That means for such a system I know all these quantities, omega n is known, C by Cc is known, and with different values of omega 1 I would like to find out what is the amplitude response. If you look at the phase information, so we can similarly show that I can write phi in the same fashion as we did here. It will be inverse tan or tan inverse of the following quantity, 2 into C by Cc into omega 1 by omega n divided by 1 minus omega 1 by omega n whole square. So, you see that this we can call as 2. And in fact, I am going to write another equation which is also useful, and if you go back and see the acceleration due to x1, what is this? This is nothing but d squared x1 by dt squared, that is the acceleration of the table at any given instant of time because of the vibratory motion of that. So, this can be written as d squared by dt squared of x naught cosine omega 1 t, and this will be nothing but minus x naught omega 1 squared cos omega t. That means that the acceleration of the because of the vibratory motion is proportional to the amplitude of the motion multiplied by the square of the frequency of the change. Omega 1 squared is the frequency change. So, I can interpret the equation number 1. Equation 1 may be also interpreted in terms of acceleration response. And we will go back to the equation and see how this interpretation is done. There is already omega 1 squared here. So, all I have to do is you take this omega 1 squared out, because that is proportional to. So, x2 minus x1 divided by x naught, if I take out this omega 1 squared because that is the acceleration, you can see that 1 over omega n squared multiplied with this whole thing is going to be the response due to acceleration. Therefore, equation 3 I can write down, and what I will do is I will, because omega n is a constant for any particular system, I need not worry about that. I can say that the response, acceleration response is given by the factor. So, the acceleration response equal to, I will use the symbol k for that factor. I am removing that omega n squared from that expression, and I am going to say that this equal to 1 minus 1 over square root of 1 minus omega by 1 by omega n whole squared, square of this, plus 2 into c by cc into omega by 1 by omega n whole squared under the square root. So, we will call this expression as 3. So, in the next lecture I am going to start from these three expressions and describe how an accelerometer or a force measuring measurement instrument can be designed either for measuring the amplitude or the acceleration, as the case may be. Thank you.